In this lecture, we are going to learn about heap sort. Okay. So first, we will learn about heap data structure, and then we will look at heap sort. So, first, what is heap? So heap is a tree that has the property it's nearly complete binary tree. Okay, so it's nearly complete binary tree. So what's the meaning of nearly complete? So tree that is completely filled at all the levels except the lowest level. Okay, in which case in the last level it is filled from left to right. Okay, so it means that all the levels, like these levels, level 1, 2, 3, 4. So this has 4 levels. So 1, 2, 3 all are filled completely, but the last level might not be filled completely, but it can be partially filled, and the node starts to be filled from left to right. So in this first level is filled completely. In second level we have 2 nodes, so it's filled completely. In third level also each node has 2 child, so it's filled completely. But in the fourth level we see that okay, there it's not filled completely. There should have been 8 nodes, but we have just 3 nodes, and they are from left to right. So this is a nearly complete binary tree. So heap is a nearly complete binary tree. So this is the first property. And the next thing is, if we put index on it, so it will be, this node is 1. If it has index 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10. So we are numbering each node, and we number the first node at the first level first, then in the second level from next to left to right, in the third level from left to right, and in the fourth level from left to right. Okay, so when we make an array, so this has 10 nodes. Okay, so 10 nodes are there. So if we make an array, so this is 20, 14, 12, 8, 6, 9, 2, 5, 4, 1. Okay, so these are the numbers, and if we give them the index, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 nodes, and if we see, so this is the parent, this is its left child, this is the right child. So for node 1, so its left child is this, and its right child is 12. Okay, so similarly, let's see for node 2, the left child is node 8. So this, and right child is node 6. Okay, so this one. So next we see for, let's say, for node 3, which is 12, so its left child is 6. Okay, so for 12, so we have node 9, so this is the left child, and 2 is the right child. So what we see, a beautiful property, that if the node is I, then its left child is 2i, this case, and right child is 2i plus 1. So if any node you take here, so this, let's say this one, node 8, so its index is I is equal to 4. So its left child is left of 4 is 8, and right is twice into 4 plus 1, which is 9. Okay, so left index of a child of a node I is 2i, and right is 2i plus 1. And similarly, the parent of a node I is I by 2, the floor of I by 2. So the parent of this node 6 by 2 floor, so it is floor of 3, so which is 3. And for this one, the parent is 7 by 2, so it is floor of 3.5, which is 3. So, okay, so this is the property for finding the parent, left and right of any node. Okay, so now let's see there another property, that is maximum heap property and minimum heap property. So what is max heap property? So max heap property is that the value of parent of a node is always greater than equal to the node value. Okay, so that is max heap. And for min heap, the value stored in the parent of a node I is always less than equal to the given node. Okay, so minimum element hence in a min heap will be what? It will be in the root, because the parent value stored in the parent is always less than equal to its child. So what about root of a max heap? So if we see, this is a max heap because for each node you see that, okay, so this parent, the value of child, these two 14 and 12 is less than 20. For this node if you see, so 8 and 6 are less than 14. For 12, so this 9 and 2 are less than 12. For 8, 5 and 4 are less than 8. For 6, 1 is less than 6. So we see for all the nodes this max heap property is satisfied, and hence this is a max heap. Okay, so this is the max heap. And what else? The root, because it's the parent is greater than both the child, so the root will have the maximum value in a max heap. Okay, so now let's try to see one problem we will see. So given a sequence of numbers in an array, so this is an array, so 20, 16, 14, so till it goes its max heap, just check if it is a max heap. Okay, so this is our question, we have to check if it is a max heap. So what happens? So this will be index 1, this is index 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so if we put it in form of a heap, so what happens? 20 is the first node, 16 and 14 are the left and right child. For 16, what happens? So this is index 2, so index 4 and 5 are its left and right child respectively. So we construct a tree like this, and to find if it is a max heap, so what we need to do? So for each of the nodes we will see if its left and right child are less than the node. Okay, so for 20, so left child 16 and right child is 14, so they are both less, so this is fine. For 16 or node 2, so this 6 and 13 both are less, so this is fine. For node 3, value is 14 and 10 and 1 both are less, so this is also fine. So for node 4, so 6 is the value and 5 and 7 we see, so this is not correct. Okay, so this is wrong, so it's not a max heap. So max heap property is not satisfied at node 4. Okay, so this is the problem. So max heap condition not satisfied at this node. Okay, so now we will see that, okay, if this is the case, can we correct it? Okay, so can we correct this? So one thing we can do is that, okay, if I put 7 here, okay, and 6 here, so now it becomes a max heap. Okay, because now the parent has higher value than both its left and right child. So now we will see an algorithm that, okay, if we have a binary tree and that is a heap we have, so how will we correct it to make a max heap? So this is the algorithm. So we will take a look at the algorithm. So what happens at each node? So if you are asked to, so this is maintaining the heap property at a given node I. Okay, so array is also given for the heap and the node index is given. So we have to check that, okay, for the heap starting at this node, so is the max heap property satisfied, and if it is not, we have to correct it. Okay, so what we do? So we find left of node I and right of node I. Then what we need to check to see that if the max heap property is satisfied. So we check that, okay, first thing is that, okay, heap size is the total number of nodes in the heap. Okay, so heap size is for this node is 10. Okay, So heap size, so of course, so left child index should be less than equal to heap size so that it is in the tree itself. And if the value of the left child is greater than ai, then we say that okay, max is equal to L. So that's the case. Then we check with the right child. So if R is less than equal to heap size, so it is in the heap, and A of right child is greater than A of max. So this checks if right child is greater than both the left child and parent, then max becomes R. Okay, so now we have the max, that is the node index of the node with highest value. So if max is not equal to I, so what we do? So swap ai and a max. Okay, so we swap the parent value with the maximum value among the left and right child. Okay, and then what we do? So now the max heap property is getting satisfied at node I, but it might be a problem at the swapping. Because of swapping, the smaller value has come to that node. So now we want to correct that. So we call the function again max heapify a comma max. Okay, so let's see how it is happening. So few things we observe. This is a recursive function. Okay, because we are calling the same max heapify here. And what we are doing? So we are now doing max heapify on a child of that node I. Okay, and it can be the left or the right child. If the thing is that if the node has value greater than its left and right child, so this recursion will not be called recursive call. But if it is less than the left and right child or any one of them, then we call max heapify on a comma that node. Okay, and we also do the swapping. Okay, so we swap a of I with max of a of 2i and a of 2i plus 1. Okay, so that's what we do if ai is less than any of them. So let's see with one example. Okay, so in this question, so we are asked that okay, max heapify a comma 3, and array is given like this. So we construct the tree. So this is 27, 17, 3, 16, 13 and all. So we have a tree or a heap which is given, and now the question is max heapify a comma 3. So let's try to solve this. So a comma 3, which means I have to max heapify this node. Okay, so again, max heap property is that parent node value should be greater than equal to the left and child, both the left and right child. Okay, but here we see that a of 3, which is 3, is less than 10. Okay, so what we do? So we swap the value with the maximum among the children. Okay, so 10 is now, so we swap 10 and 3. Okay, so now what happens is, let's try to do, so 10 and 3 we swap. So it becomes, so 10 and 3, so 10 comes here and 3 goes here. Okay, so now we see that okay, this is done, it is fine. Now this node is now greater than its left child and right child, but some lower value we have put here. So now is this node satisfying the max heap? So 3 we check now with its left child and right child. So now it's not satisfying the max heap property here. If it was 10 here, then this max heap was getting satisfied, but because we percolated it up, so now with 3 this property is not getting satisfied. So what we do? So let's see, this is 3, this is 8, this is 9. So why do we swap with the maximum among the children? Because if we swap with the minimum, it will be 8, 3 and 9. So now with this the max heap is following, but with 8 and 9 it is still not followed. So hence if we do with maximum, then it is 9, 8 and 3. So max heap is getting satisfied. Hence what we do now? So 3 we swap with maximum, that is 9. Okay, so 9 comes here and 3 goes here. So now what happens? So this is now satisfied and now max heapify we don't need to call because it has no children. Okay, so what will happen, how is it taken care of? So L is less than equal to heap size is not followed, L right R is less than heap size is also not followed for that node, and hence it will come back. So we see here, so for this node, so its left is 26 and right is 27 and the heap size is just 14. So now recursion will stop, and now this is max heapify a comma 3 is done. So this is the basic introduction about heap data structure, and in the next lesson we will learn about how to make a given array heap in O of n time. Okay, and this will take O of n. Okay, this max heapify for any node I, so it will take O of h, where h is the height of that node. Okay, so because you can see again that it's every time we are having the size of the tree which is smaller by 2. Okay, because we are leaving the whole of the left or the right subtree. Okay, so hence for a max heapify, if we are at node I, then the height of that node, so our max heapify will run in O of h time. So I hope you understand the concepts of this heap and about max heapify, what is the minimum heap property and max heap property. So next we will